Let's see. Yeah. So I met. So we were able to get out of. We were able to get done with this pretty early. With the. So we got done with the practice exam fairly early with the evening class. So we'll see how it goes there. But a lot of you do. So about half the class has the exam. Half the class has the exam tomorrow. Half the class has the exam on Friday. Some of the questions. I'll go over the questions. It shouldn't be too bad. So again, it's going to be 105 points. There will be a 1.3 freebie at the very end, but other than that, you've also got essentially again, you've got this automatic 5-point curve that I throw in. I find that works out fairly well. I don't know if it's too generous, but heck, I'm not stopping this semester. Maybe next semester or so. Final's not going to have that. In response to a lot of people, yes, you are allowed one sheet of notes, front and back, A4 or letter, handwritten or typed. Right, so and if you get really fancy and you need to print out like something so small that you need like a microfiche reader to read it, just don't make too much noise if you have to drag a microfiche reader to the classroom. But regardless, whatever detail you need to put into it, just put it into it. My suggestion though is from seeing this happen a bunch of times with students who are not doing well with the class, do not just okay, it's fine to write all the stuff, all like the code that I'm going to go over today on the exam and stuff from your previous assignments, but don't just blindly copy and paste the code from your notes onto the exam in the hope that it's going to work, because I'm going to go with that looks like gibberish. Oh, it looks like gibberish because he copied the answer from a question that wasn't on the exam. Well, that's completely wrong. So, all right, and yeah, it's going to be a bulky exam, but that's because there's just going to be a lot of drawing on it. Okay, right? I give you an entire page. I think this is worth 7 points rather than 5 points on the exam. Same with this one; it's worth like 7 than 5. So, and you get plenty of space to do that. So, and you'll also note that this was a lot less there was a lot less coding on this exam and more theory on this exam. And that's just because there's so many concepts to test you on, and I've already tested you on coding in the timed lab. So some of the aspects of the timed lab I like, some of them I don't like. So informal survey: how many of you hate the timed lab with a passion of 1,000 suns? A couple of you utterly hate the timed lab. A good.
Is that like the concept of the timed
lab? Okay, so I suppose this is another thing. How many of you hate the entire concept of a timed lab? Okay.
Timing.
Yeah, the whole. So yeah, right. So you hate the pressure, in other words, right?
I love the keyboard.
but you like the keyboard, right? So, and how many of you are like, I don't like it, but I mean, they just merely dislike it, right? No, not hatred there, just dislike. And how many of you are just, it could be worse, right? So, right, because I don't think anybody likes it, right? So I'm about half split between students who are willing to tolerate it and half students who do not like it, right? And students who are even opposed to the concept of it. Now, the reason we are having timed lab this semester, just to bring it up again, is because your exams used to have had more weight to them, like they'd be worth 20% as opposed to 15%, and the final was worth another 5, more on top of that. And one of the complaints I got from students in my feedback was, hey, can we? Which, by the way, I actually read was hey, the exams are way too stressful because there's so much weight on the exams. I'm like, okay, so maybe I can pull it out into more exams, right? The more exams, and maybe if I have a less high stakes exam, right? That was kind of the idea there. Now, 1068 is going through this too, but they utterly hate it because they only have an hour to do theirs, as opposed to the hour and a half I think I give you guys. So So there's that, but I think the second time lab was better than the first time lab. It was a bit more coherent, I feel, and it had a number of freebie questions on there. So what improvements could be done for the timed lab if I were to continue them on for 2168?
I mean, I'm always gonna say more time.
More time, right? Okay. Sorry.
I feel like it's a concept by concept based question. Because some things take longer to code, but like most of the stuff was recursively done, so it takes less time to
Right.
code it overall on the last one. I think that was what was the problem with the first one compared to the second one was just how long it takes
To actually physically type it, and I think that's an excellent point, by the way. That's basically the amount of time, the physical typing time it takes was much less than the last one because recursive problems, by their very nature, take less time to code. Okay. Yes.
But if you can't figure it out, then you can have 10 hours and
then you
Right.
do
that's
what-
I think what you're saying is.
Right.
I think that's what I mean. Because even having it be like some short form of coding, at least allowed it so that you had time to actually think about the problem.
Right.
Versus if you had to code for a significant amount and then you were thinking about the problem
Right.
beforehand.
And then we get into the issue. Okay, so I give you one problem, and then it's a one or nothing.
Maybe you can tell what the topic of the lab is first, because then that allows something.
Did I? I mean, I thought I mentioned. I thought I mentioned for this one. I think for the first one it was a bit more abstract because it was just, oh, it's array problems, but you're doing them on lists instead, right? Which wasn't too much help. Right. So that's a good. That's a fair criticism. You see, I'm open to criticism and the way and the changing my class. We will have I have an idea for what our third and final time lab is. And this one, my idea is I'll do the same one that I've done, a homework assignment I've done for the past couple semesters here that I really like. The difference here is that this problem will be able to be done by hand. So that makes it a bit different, but it's going to be a graphing problem. It's going to be a graph problem. And I think this, if we do the one I'm thinking of, you can do it by hand. The other one is that we might do a sorting time lab, but it's going to be reversed because you don't code. A typical homework assignment is code sorting, given a sorting algorithm, code this up. I might do something along the lines of, that's the reverse. Here's a sorting algorithm, figure out what sorting algorithms these are. So that might be so those are the two possibilities. Either a graph problem given at the end of the semester or a coding problem given in a couple weeks about sorting. So, but that's timed labs. Don't worry about them for right now. Again, your homework has been extended until Monday. And again, I went over about how to solve those things, that homework on, and again, work with your partner on that. So I'll go. So with the time labs, I'll definitely take this into consideration. I mean, if I have, we'll see how that affects grades because I don't really know how. And I gave them my TAs a reminder to finish up grading them, right? So that we can actually, because once we grade the two timed labs and we have 2 exams, I actually have a really good idea of how those are going to affect people's grades and what your final grades will be, because they don't really move too much with regard to the final exam. At least that's my hope. All right. So this is a series of questions that will be on on both this exam and on the final exam, because, or at least I'm pushing to have it on the final exam in the meeting we're having today. And I'm writing the final exam, and they seem positive about these ones. So basically, given a bunch of scenarios, please choose the data structure that corresponds to the scenario. And on the exam, I put, you may justify your answer with no more than a sentence. Okay, right? Just in case you aren't like, you feel maybe I didn't think of a way to use the data structure you mentioned. Okay, but I tried to be pretty explicit about about the best way to use it. But if you feel like you need to justify your answer, right? You are always allowed to clarify the answer you give. All questions are essay questions, including the multiple choice. In other words, you can argue the heck out of your answer, but you probably shouldn't need more than a sentence to do so. So, which of the data structures should you use for each of the scenarios? You need to model which patient should be seen next to the hospital. Patients should be seen in as close to the order of arrival, but patients in more severe situations should be seen first. Yeah, the priority queue. If you had put heap down, I'll take it. That's not wrong. I mean, the heap is used to build a priority queue, so I'll take heap as well, right? Even though it's not up there, but I'll understand. Like if you put hash table for something that needed hash table, I'll accept that. That was a map. I'll take hash table as well. A router needs packets to hold a buffer and deal with them in the order they appear. Yep, that's a queue, because when you're dealing with stuff in the order they happen, that's a queue. A stack is dealing with stuff, in kind of the reverse of the order that they happen. You need to model hierarchy. This one was a bit more abstract. Yeah, it's a tree. Notice that I put tree up here rather than binary search tree, right? Okay. Hierarchical stuffs. When you're sorting things by hierarchy, that's a tree is very useful for that. You need a data structure to hold your previous decisions in case you need to backtrack. That's definitely a stack, right? Backtracking and stack. Do not put recursion. That is flat out wrong. I've seen that on the final exam, and that's just very painful.
Would trees kind of work for backtracking because trees kind of do backtrack in a sense?
I think your argument makes more sense for a graph in that case, but you would want to still use a stack for backtracking. If you put a tree and a justification, you'd probably argue yourself into half or 2/3 credit.
I should really like backtracking into stacks.
Yeah, stacks and backtracking. Those should be two things that are mapped together.
And then for three, instead of tree, why would you specifically say so? Like the reason, I think I know why.
Because trees are useful for modeling things from a top-down relationship, right? In real life, right? In a lot of things though, it turns out that hierarchies are complicated, and you might actually say, oh, that's more of a graph because people can report to multiple people, right? Because bureaucracies can be really crazy, but and that's a fully valid argument that basically human relationships are too complicated to model with a tree. So speaking about relationships and vocabulary, yes, 4 was a stack. A stack, right? So on the actual exam, what I'll give you is I'll give you an actual tree. I'll give you a tree, and I'll say, okay, what is the relationship between these two items? What's the relationship between these two items? It's a bunch of fill in the blanks with these kind of things over here. Each of those are worth a point each. Don't really freak out about it. I'll ask you to modify the tree slightly, like basically add some stuff or cross some stuff out to change the tree a bit. Just so you can so basically this page and the next page go together. Okay. And this one is out of place here, and that should send up a warning flag. So the top of the tree, so the node at the top of the tree is called what? It's called the root. Okay. The links from a node to its successor are called what? Sorry? Children. Yeah. So, well, not children. Not children. That's a link. The links to the children are called what? Branches. Branches. I'm not but if you call them links too, I'll probably take the answer. The links to the children are called links. Of course, what you call a special type of hot dog. It's a gourmet hot dog, or just a hot dog, right? It's not really anything special. So, all right, what is the predecessor of a node in a tree is called what? Your parent, right? Your predecessor is your parent, and if you have the same parent, your siblings, right? So remember basically also that there's the ancestor descendant relationship if you want to abstract that out. If you would put ancestor in there, or so if you put ancestor here, I would have gone, that's technically correct, the best kind of correct, right? So right, so now describe using code how to calculate the height of a tree recursively. So first off, what is the definition of a height? Of the height? Yeah. Well,
yeah, the length of the longest
the
path.
length of the longest path.
The root to the leaf.
That's right. It's another way to view it is what? Distance from the root plus 1. So the height of a tree. So the height of a tree with So the height of this tree is 0. It doesn't have a root. So, but this guy, this single node, his height is 1. The distance, its height is the 1. Yeah, the length of the longest path is 2 here, but it's the lowest level, right? Plus 1. So in other words, so here's a good question. How could I figure out the height of this tree? And let's say this height of this subtree is 5 over here. Okay. How can I figure out the height of this tree recursively? Yes.
For any specific node, give it a method that returns the largest number of the height of the largest child tree.
Yeah. You figure, or better yet, it's easier if you break it down into the steps. Like you say, okay, if I figure out the size of my left child, figure out the size of my right child, the height of my left tree, figure out the height of my right tree, right? And my height is the bigger of those plus 1, right? So here, Root doesn't know his height, so he'll ask his children for their height. So he'll say, let me figure out my height by asking my kids. Let me switch this view. So his height so he'll figure out his height. This guy's height is 0 because the base case is if I've got no node there, my height is 0. So he'll go 0, 0. So my height is 0 is the max of 0, which is 1. It says his is 1 over there. So the bigger of 1 or 1 is 1. So my height is, I guess, 1 plus 1, so that's 2. So I'll return that there. So I've got the height of my left tree. My right tree will go, I get the height of my right tree, he'll go 0. And my right side is 5. So 0 versus 5, I'll take the 5 and say my height is 6 because that's 1 more, right? And then, so I've got now 2 and I've got 6. So my height is 7, right? It's 6 plus 1. So to find the height of my tree recursively, calculate the left, calculate the right. This might show up on the exam. Just as a warning. So yes.
You want us to describe the base case also?
It would be useful there to figure out what the base case is. Okay. So draw an example of each of the following types of binary trees. Use a different example for each possible tree. Full, complete, perfect. Also, there's balanced binary trees, which we haven't defined yet. You're going to have to wait till the exam to find out what that is. So,
Wait. Which one isn't defined yet?
balanced.
Okay.
No, I've never actually defined what balanced formally is. I don't. Yeah. So you'll find out what that definition is on the exam. So that's I'm not saying it's not saying you have to know it. I'm just saying that the definition will be on the exam. So draw an example of each of the following binary trees. Use a different example for each possible tree. So a different example because I guess technically, I had to specify a different example because technically I could draw a single circle, right, a single node for all of those and say this is a full tree, this is a complete tree, and this is a perfect tree. Okay, so I guess then we need to ask ourselves, so what does it mean to be a full tree?
No, it means that the leaves or like the outmost outer part of the tree has 2 children. Actually, besides them, every node has 2 children.
Right, everything but the leaves has 2 children.
Yeah.
Right, every node has either 0 kids or 2 kids. Right, so this is a full tree because every node has 0 kids or 2 kids. Right, this is not a full tree because he's only got 1 kid. He's got space for 2. This is a full tree now, and this is a full tree. And this is still full over here, right? Every node has either 2 or 0. It doesn't have to be symmetric, okay? So complete trees, really important to know these because you should need to know that that's the shape of a heap. Okay, complete trees are really important because that's what we're going to use for heaps, and heaps are super important because they're worth 14 points on the exam, and they're very common for students who focus too much on the other stuff and forget about heaps. I see it all the time. Basically, students do great, and they end up with a B because they completely forgot about heaps. And it's kind of tragic, but I warn you. Okay, so complete trees, right? They are essentially, you know, they look like those beautiful, perfect trees that we are going to draw in a bit, right? Except up to the bottommost level. So this is a complete tree, right? And complete trees, essentially, I can go through them right to left and kind of like just store them in an array without any gaps. Is kind of the idea. So in like 0, 1, 2, 3, 4, there's no gaps in there, right? If it was like this, it would be 0, 1, 2, 3, gap, you know, and then 5. There'd be a gap there, a null there. Complete trees aren't going to have that null in there. So they're filled up on this level, right? But the bottommost level, it's not necessarily all the way filled up, but there's no gaps going left to right. So this is complete, this is complete, this is also complete, this is complete, this is not complete, nor is this, nor is this. Nor is this, but now this is now. But this is complete, this is complete, this is complete, right? If I remove this node, it's no longer complete because there's a gap there on the bottom, right? So looks nice and perfect all the way on top, and then it's just being filled left to right. Yes?
Is it perfectly acceptable to have a positive, like this is a complete example, and then this is a not a complete example
Yeah.
next to each other?
Oh, yeah.
So we showing that we understand the
Yeah. Yeah, in this kind of case, it would be. For this question, I don't know if that will necessarily apply in the question for the questions we are going to ask. Yeah, this isn't your exam, so no worries about that. But so a perfect tree. Perfect trees are of height h. Okay, and then they have 2 to the h minus 1 nodes in them. Okay. So 2 to the h. Height, and then 2 to the h minus 1 nodes in them. And that's just a mathematical definition for that simply says they look pretty and nice and full and balanced and stuff. They look ideal, right? They look like basically the bottom level is completely filled up. The next perfect tree of height 4 would have 15 nodes, right? 2 to the 4th minus 1. So it would have 15 nodes in them, and it would look like this. Every node, you know, it's just completely filled like that. It looks like a pyramid, right? Without any spaces missing, right?
Sorry, what was the formula?
2 to the h minus 1. 2 to the h, right, minus 1 on the outside of that. So, right? So if you've got a height of 4, you're going to have 15 nodes in there. Right? So here's height of 4. So 1 plus 2 plus 4 plus 8. So 8 plus 2 is 12. Sorry, 8 plus 4 is 12. Plus 2 is... It's a binary tree, right? 16 minus 1. Yeah, 14 plus 5 plus 1. Okay, so this next question is a great preview of what's going to actually be on the exam, because this is the exact, I think this is the exact same, almost the exact same wording as that I have on the exam. The only difference is that you've got different numbers. That's literally the only difference for this problem. You have different numbers for this problem. For the delete method, it's slightly different because what I'll do is I'll give you a tree and tell you to remove items from it rather than using your previous answer. But here, I was lazy and didn't want to make another tree, and I just simply said use your previous answer, okay? So here, draw the binary search tree that forms after you insert the following integers, okay? So basically, just create a binary search tree, so it's going to be sorted from scratch, basically. So, and 42 is going to be the root of that tree, okay? That's what we mean, right? Because you start out with 42, and so we get 42 over here. Okay, so now we have to insert. This should be a pretty easy thing if you understand how this works, right? So 10, we need to insert 10 into this tree. 10 is less than 42. It's easy to make a minor mistake there, and we'll kind of be able to recognize a minor mistake versus you completely don't understand, right? So 10, that just simply depends on like where and how many errors occur and where they occur. So 42, put in 10 next. 10 goes to the left. 50 goes to the right because it's greater than 42. Okay. 12, and there's a lot more in here than I would probably make you have, and you can break it up into steps, right? You can draw like step by step if you needed to, or if you need to, but that's more useful for delete rather than doing insertion. So 42, 10, 50, 12. 12 is less than 42, but it's greater than 10. Goes here. 17 is greater than, 17 is less than 42, greater than 10, greater than 12. So 17 goes here. Okay. 80 is bigger than everything we've had in the tree. Bigger than 42, bigger than 50. So 80 goes here. Negative 12 is smaller than everything we've seen in the tree so far, so it goes here. 100, bigger, bigger, bigger. So 100 goes over here. And don't worry if you're not like, lining things up perfectly. I mean, I didn't last night when I was going over the exam. So what we care about, we'll be able to tell if you're, we'll look at the shape and go, yeah, that's right. And then if we have to double check it, don't worry about it. Really, we care about the lengths. So now we've got 190. So now we did 100. Now we do 96. So bigger than 42, bigger than 50, bigger than 80, smaller than 100. So 96 goes over here. Okay. 105 goes next, and that's bigger than everything else. So bigger, 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 bigger. 105 goes here. Right. You always insert it as items as a leaf. 86. So bigger than 50, bigger than 80, smaller than 100, smaller than 96. So 86 goes here. Right, and 72, bigger than this, smaller than this. So it goes, and we hit a leaf, so we go over here. So this is the answer for that. Right, and this is worth like 7 points. It should be like nice 3 points for you guys. Okay, using your previous answer, I'm just making sure that I didn't skip something. Okay, using your previous answers. So the next question is, using your previous answers, draw what happens when you remove the following. So first we're going to remove 42, then we're going to remove 12, then we're going to remove 17, and then we're going to remove 96. I have you remove 4 here. I think on the exam I have you do 3 removal operations on the tree. Okay. So let's remove 42 first. So first we have to find 42 in the tree. Done. It's the root. Okay. Next we have to ask ourselves, what case are we looking at? And that depends on how many children I have. Okay, how many children does 42 have? It has 2 children, which is the hard case, right? So if I'm removing no children, it's pretty easy. I just remove it. If I'm removing something with 1 child, my parent adopts it, right? And if I'm removing something with two children, I find the next in order predecessor or the next in order successor. I'm going to go with the predecessor because that's what I've been teaching. So that means I'm going to find the biggest the biggest thing that's smaller than me. So the biggest thing that's smallest than me, that means the biggest thing in my left subtree, right? Because the left subtree has all the things smaller than me, and I want to find the biggest thing in there. So how do I do that? Well, I would kind of just look at the tree and say it's 17. But how do I algorithmically do that? I go 1 step to the left, go all the way to the right. So I go and find 17, and I'll have 17 replace me. And then I remove my old 17, right? It's kind of the idea. How do I remove that old 17? Well, it's got no children, so I just kind of just erase it, right? Okay. Now I need to remove 12. 12 is no problem to remove, right? Find 12 by going there. Don't remove the negative 12. I mean, if you do, that's kind of an understandable mistake, but, So we remove 12, and it has no children, so we just kind of just do that, right? No problem. 17, okay, we're removing the root again. So now we got to find the biggest thing smaller than me, and I like this one because I say go 1 to the left and all the way to the right, and most people freak out because there's nowhere to go on to the right. Well, you went all the way to the right you can, right? This is the biggest thing that's smaller than you. So this is the guy we're removing. So we copy this over, right? And now we got to remove the old 10, right? But it has 1 child, right? So what do we have to do? The parent adopts it. So you can either draw your line like that, or you can do negative 12. Okay. Okay. So the rules are very consistent. So let's go through that rule again by removing 96. So find 96, right? 96, bigger, 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 smaller, found it. Okay, removing 96, that means I remove I'm removing a guy with one child who has a child, so I just simply adopt that child, right? So removal really have three cases for doing that. You know, either you're removing one child, which is easy. So you're removing something with no children, which is easy. Something with no children, which is almost as easy. Or you're removing something with two children, which is your entire goal there is find your next in order predecessor, copy that over, and now you've reduced the case, and then you delete the old item that you copied over. And in that case, you just reduced it to one of the easier cases, right? Okay. No.
For the answer, you could just be looking for the final tree rather than like.
So that's your decision there. I highly recommend like doing it step by step, even though that might take longer, because then I can give you partial credit if you mess up somewhere. But if you give me the final answer, I'll just take it. Sure.
Can we like shorthand it a little bit? Like since it doesn't ever touch that bottom tree of 50, can we just have it as like almost as done?
Yeah, you
So
could.
the first two just do like the little triangle.
Yeah, you could. Yeah, you could. I suppose. Yeah, that's fine. I guess on the last answer, it would be. I'd really like to see
Then I
that.
do the full tree. At that
Yeah, just to make sure that I understand it, or that we understand that you understand it.
I think I got lost in removal, sort of.
Okay.
So,
At what point?
so you like removed, I think.
17.
Yeah, 17. You put it in the root. Why would when you remove it? Are you removing it from the tree, or you?
Removing it from the tree.
Okay.
Right. So when we did when we deleted 42, we had 17 come up to be the new root, and then in our instructions later we had to delete 17, which was now the root. And so
Is the root not part of the tree?
it is part of the tree.
Oh.
It's just the topmost one.
Okay.
And every node is the root of its own subtree.
Right. Okay. So okay. I'm just not getting something. Right. So could you go over what happens? Like you can just resume with this tree. Could you like kind of go over it just one more time? I guess.
Sure. Let me draw this over here, and draw. Let's draw 5 over here. Okay. So say I'm going to remove. So say I want to remove. Let's see. I'm just trying to look for a good candidate over here. I want to remove 7. Let's go with 80 from the tree. What?
That's exactly what I wanted you to do.
So let's go ahead and remove 80. So we search for 80 first. Okay, we found 80. Okay, and so now we have to find the biggest node that's smaller than me, and that's going to be located in my left subtree. Okay, so I go 1 to the left and all the way I can to my right, which doesn't bring me anywhere. So I found 72. So this node is going to be replaced by 72. So the way we get replaced is we copy this over, and then we delete the thing we copied over. So we delete the extra copy of 72.
Yeah.
So now, and to do that, we ask, okay, does it have? It has no children. Okay, no problem. We just erase it. Okay. Now, if it did have a child, like 65,
Okay.
it's only ever going to have one child if it has a child at all. Because if it had a right child, we would have used that to be our replacement, right? But for this one, we're deleting this guy. It has one child, so we're just going to have the extra copies parent adopted.
Okay. What happens if there's a right child to that previous 72?
To the previous 72.
Yeah.
So 80. That's an excellent question. 73, like that. Well, in this case, we aren't going to delete 72. We're going to delete 73 instead because you go 1 to the right. So you go 1 to the left and all the way to the right. Right? That's always going to. And this one, and we know that 73 is not going to have a bigger child in it because if it did, we'd go further past 73. Right? So you're never going to have a right child there if you're looking for your next in order predecessor. You always just go as far as you can until there is no more right child.
Okay.
That makes sense?
Yeah.
Awesome. So, all right. So now for the other thing, traversals. Which of the following is the order for pre-order traversal in a binary tree? with some of these left and right. So in order, right? So we've had these orders here. So this top one, if we look at that, that's the in order, right? We do the left first, then we do ourselves, then we do right. Okay? So what's so which one of these is pre-order? Yeah.
B.
B. We do ourselves first, then we do left, and then we do right. Okay? C is what? That's post order. And D is something, right? It's wrong because we always do the left tree before we do the right tree. Right? So going down to this one, what is the post order? Well, that's where we do ourselves last, and so that's C, right? So be sure to know your traversals. Okay, so heaps. The heap question on the exam will be much more like the tree questions I just gave you. Okay, but I have you I'll remember the algorithm in detail over here. So it's going to be much more like, here's an empty heap. Add like these 5 to 6 items to the heap, right? So you might want to practice that, but that's what you'll have there. So first thing I want to talk about, though, because I have this first, the removal part first, which is also something I have to do, because this is where a lot of students I see mess up. How does removal from a heap work? First off, what items can be removed from a heap? Just one, the top one. That's it. You can only ever remove the top item from the heap. So the question I have on the exam is like using the heap you just drew, remove 2 items from the heap. And then I get weird and wild answers because students don't remember that you have to remove the root of the heap. Right? So the removal operation always removes an item from the heap. So how does the removal work if you're removing the root? What does it get replaced by? Let's see. So let me go ahead and draw a heap on the board because that's going to give us something actually to work with rather than dealing with abstraction, which is always terrible, right? Because right. So we've got. Actually, I won't put circles around everything because that just takes more time. So we've got 0, 1, 2, 3, 4, 5, right, 6, and then 7 over here. So this is a heap, right? It's a minimum heap. Every item is smaller than its children, right? And then that applies for the entire structure. Okay. So if I were to do a removal operation, I'd remove 0. And what do I do? What do I replace 0 with? 7. I replace it with 7 because it's the last item in the heap, right? The heap, if you remember, it's got an underlying array, right? You remember it's got an underlying array, and so we take the last item in the array and move it to the front. And now we have to reheapify it, right? And the way I describe it is like heavy items sink and lighter items bubble to the top. So heavier items sink, so 7's going to sink. So 7 needs to swap with the lighter of its children. So swap with 1. So 1 needs to become the new root. And then 7 needs to swap with 3. So notice that it doesn't necessarily have to be in order like I had it. It just needs to fulfill the heap property, which is that a parent is smaller than its children. Okay? So that's how removal works. If I were to remove 1 as well, right, we'd replace it with 6. And then 6 would need to bubble down, so we'd swap it with 2. And then we'd swap 6 with 5. Right? Now, what's important is that we maintain a complete binary tree in this. Okay? I sometimes get students who will give me heaps that look like this, like something like this, and we just kind of just mark this wrong because without really even bothering looking at it, because you missed the point of heaps, which is that their shape is always a complete tree, right? So this would be utterly wrong because it's okay. So it's got to be a complete binary tree. So how would I add, say, the number 10 to this heap? where does it go if I'm adding an item to this heap? It goes to the end, the last position in the complete binary tree. Basically, the next location that you got to keep this thing being complete. So you add it basically to the next location that would keep it complete. If I were to add 11, go to the next level over here. Okay. Now if I were to add, let's say, if I were to add 1 to this binary tree, sorry, to this heap, I'd put it here. But now we have the issue where we've got a parent has a child that's smaller than it. So in this case, right, when you add an item, you're not just it's a two-step process. The first thing is you add it to the end, and then you swap it with its parent if it's smaller. If the item that you just added is smaller, and you just repeat it. So 1 and 3 will have to swap as well, right? Because the smallest item just bubbles to the top, right? So add an item, and so when you add an item, let it bubble to the top. You add it to the last location of the complete tree, and then you let the lighter item bubble to the top. When you remove an item, you remove the root by replacing it with the item from the bottom of the tree. From the last location, you take the last item and remove it so that it maintains its complete property. Put it at the top of the tree, and then you let it sink as far down as it goes by swapping it with its smallest child. And once it hits bedrock, you're done. Or once you hit children that are bigger than you, you're done. Okay. So know how to do those because those are fairly important. All right. Next we have Huffman coding, right? Which will also definitely this will definitely be on the final. And also this has been constructing a heap using an algorithm I'll teach you in a bit later, using turning an array into a heap. We'll teach you how to do that, but it's also been on the final in past semesters. So, all right. So drawing a Huffman tree for the symbol. Let's go ahead and see. So we've got A is 50. So we've got this frequency table, and we've got to put it into a priority queue in the order. So A is 50, P is 40, L is 20. We're doing the Huffman encoding queue, right? So here's our frequency of our characters. E is 70. We've counted up some documents, and we found E occurs 70 times, A occurs 50 times, P occurs 40 times, L occurs 20 times, and X occurs just once. Okay, so now we have to figure out our, oh, that's much better. So now we got to figure out the values here, the trees. Yes. So you've got this priority queue here. So the way we construct a Huffman tree is that until there's only one item in the tree, what do? We dequeue the first 2 items from the tree. So we've got X, and we've got L as nodes. We turn them into one node with a combined weight of 21, and we put that back into the priority queue. Okay, but you can't just add it at the end. It's a priority queue. It's going to resort itself. Oh, I should probably. There you go. It's a priority queue. It should resort itself. So 21 should go to the front. Now it's not always going to go to the front as we're about to see, but in this case it does. Okay. Now we dequeue twice. We put the first thing we dequeue on the left, the second thing we dequeue on the right of the new tree we're creating. So P combined weight of 61. So 61. So we insert this into the tree, and we're going, oh, 61. Well, that's big. That should go in between these two nodes, or these 2 items. So now we dequeue twice, 50 and 61. So first thing goes on the left, the second thing goes on the right. So, And it has a combined weight of 101. Oh, sorry, 111. Okay. And then we've got 2 items in the tree. We DQ the first one. Right, this stays on the end because it's bigger. We DQ the last one. And DQ this one. So we combine them into something that has a weight of, actually it doesn't matter at this point because we're done, right? So we have so now we have our tree. And then if we want to encode things, we mark the lefts with zeros and then the rights with ones. On the exam, I believe I give you something to decode. On the practice exam, I give you something to encode. The reason I give you something to decode is because if you got it wrong, it should generate gibberish, right? And you might have leftover characters that will give you a warning that you did not do it correctly. But if you don't do it correctly, just go back to it later. But here the question is encoding apple. So to encode apple, well, let's go ahead and say, so let's look at the combinations. E is 0, A is 1, 0. So 1, 1 is P. So P is 1, 1. 1, 1, 0, 0 is X. And then 1, 1, 0, 1 is L. So L, 1, 1, 0, 1. Oh, sorry, P is 1, 1, 1. Okay. So let's see. So now to encode apple, well, A is 1, 0, P is 1, 1, 1, P is 1, 1, 1. L is 1, 1, 0, 1. And then E is 0. And so that's the binary sequence you would transmit if you wanted to transmit apple using this encoding. All right, so now onto the coding section of it. It will be worth about 30 to 35 points, I think. You'll have 2 tree problems. On the exam, they'll actually be related to each other, and you'll want to use the first to solve the second. So, okay. In this case, they're completely unrelated to each other. And then you'll have 1 problem on maps. Yes?
Where'd you get the big one for the weight?
For the weight? The 61? It's a 61.
Okay.
My bad. Sorry, it's not bad math, it's bad handwriting. All right. So I don't need IntelliJ. We'll just boot up. Start new file. Sure. Let's call it exam.java. Save. Oh, really? You don't have a Java? Oh, yeah, you've got. Sure, you can install that while I'm working. I don't need like a full thing. I don't need a full IDE because you're not gonna have a full IDE to tell you whether you're making errors or not. So, let's see, can I start view, edit, preferences, settings, editor.font size. Geez, do I really have to change it that way? Editor dot font size.
Still better than this.
18. Oh, hey. Oh, that worked. Okay, so public class exam. So I'll put these in here. Just so I can get some auto tabbing in there. Can I? There we go. Can I like make you go away? You not really used this before, and now I'm starting to regret that fact. Okay. So public exam. The first question is, we've got write a method which, given a tree of integers, computes and returns the sum of all the integers stored in the tree. So in other words, this is a traversal algorithm, just like pretty much everything else we're going to have to do. Meaning that we're going to have to go through everything in the tree, you know, in either pre-order, post-order, or in order, in order to solve this. So public static int sum tree. And remember, the root here can be the root of a tree or a subtree. So this is a recursive problem. I mean, you're going to almost certainly have to use recursion to solve it. I think I've only seen one case of somebody not using recursion to solve it. They use a stack. So, and that's kind of like using recursion, only you just don't use a recursive method. So, public static int sum tree, basically returning the sum of all the numbers in a tree. So, for instance, if we've got a tree that looks like this, you know, 3, 7, 2, 1, 5, and 10, then the answer is going to be 1 plus 2 plus 3, which is 6. Well, it's going to be, let's see, it's going to be 10, 20, 25, 27, 28. So the answer would be 28 in this case because that's the sum of all the numbers in the tree. The question is, how do we get the computer to count that? Well, first off, let's figure out the base case since this is a recursive problem. The base case is that I've actually got an empty tree right here. So the sum of an empty tree, a tree that is null, is 0. Right? So if root equals null, return 0, and that's worth a couple points at least. Okay, and now the other case. Well, it's not null, so this is a recursive problem. So we want to figure out the size of our left tree, the size of our right tree, and the size of ourselves. So the size of my left tree, or sorry, not the size, but how the sum of the left tree of all the numbers in the left tree. So int left, that's equal to the sum of all the items in the left tree. Dot left. And my right tree is equal to the sum of all the things in my right, right? Because with recursion, I'm allowed to be lazy like this. What if my left tree is null? That's okay, I'll get 0 back. What if it's not null? Well, it will figure out its size somehow, and then they'll get back to me, right? But right now, what I'm concerned about is now that I figured out the size of my left and the size of my right, getting that information back to whoever called me, right? So let's just assume it's worked. I've got my left side, I've got my right side. Now I've got to be responsible for my job, which is getting back basically this, the left side of this tree, the right side of this tree, and then, so let's say I summed up everything on the left, that's 3, everything on the right, that's 22, right? And then I've got, so I've got 3 plus 22, and then I've got to add in my 3 as well. So return root dot, you can put dot info, dot data, dot item. I'll understand what you mean. It really just depends on what we're using. So root dot item is equal to, root dot item. So my data plus the left data plus the right data. And that gives us the answer. That's all this answer is. So I figure out the sum of my left side, figure out the sum of my right side, and my left side will do that. We'll do that as well and return the answer to me. How do I know this works? Well, let's look at the how that works in the example I just drew on the board, right? So what we'll do is that we're summing the tree up of 3. It's going to calculate the left side. The left side is going to go, okay, I don't know what my size is yet, so I've got to calculate my left, and then my right, and then I'll return the sum of that. So you go to my left. Left says, hey, so my left side is empty, so it's 0. My right side is empty, so it's 0. So I return 0 plus my item, which is 1. So 2 goes, okay, my left side is 1. My right side is 0 because it's empty. So I return 1 plus 2, which is 3, plus 0, which is 3. So I return 3 for my left side. 3. So then I figure out the sum of my right side. So 7 goes, okay, got to figure out the side of my right side, the side of my left side. Right? The left side goes 0, 0, myself, it's 5. 10, so we do 5 plus 10 plus 7. So 15 plus 7 is 22, so we return 22 back here. So I figured out my left side, which is 3, my right side, which is 22. I add those together, and I become, and we get the answer back of 25 plus 3, which is 28. And this works because, again, this solves it for any tree or subtree. All right. Everybody follow that one?
Oh, the only thing I was confused about is it says root and then it says root dot item.
Yeah. It for whatever data is inside the root, right? Right. So when I've coded up the binary search tree, you've had the left, you have the right, and then you have the item inside the tree, right?
So there isn't even a root there. That's why root is not just the item.
Well, the root is the root of the tree. It's a node in the tree, right? And I call it root to remind you that it is either the root of the whole root of the tree, or it's the root of a subtree. Okay, it's a node. You could easily just call it node instead. I call it root just because that's the naming convention I like to go by. Okay, so here on the next one, this one is, I consider, definitely a tougher question. So write a method which, given two trees or subtrees, returns whether or not the contents of the entire trees are identical. In other words, do trees A and B store exactly the same data in exactly the same way? In other words, are they exactly the same tree? So let me go ahead and draw an example and a counterexample. So tree A and tree B in this case are exactly the same according to this definition, right? They're binary search trees like this, right? Same data, same structure. Obviously, in this case, they're not the same because we've got different data in the tree now, right? And in this case over here, even though the trees have the same data, they're not equal in this case, right? Because they have a different structure. And the reason I have this structure thing is because you could do an in-order traversal of the two trees. And if you do an in-order traversal of the two trees and you come out with the same structure, then, with the same order, then that just means that the same order that the items, it holds the same items. It doesn't mean it has anything to do with the contents. And I don't know. I don't know. Do you know if doing a pre-order traversal, in-order traversal, and post-order traversal, if you did all three, would that result in the tree being exactly the same? If those traversals were exactly the same, would that mean both the trees are the same? I don't know. But I do know how to solve this problem recursively, right? How do I check these two trees are identical, right? Well, I'm going to use the same recursive case, which is that I'm going to figure out if my left and my rights are equal, and if the two roots of these trees are equal, and then I'll do that recursively. So the first thing we want to do is probably check to make sure the roots are null, just like normal, though. But because we've got two trees here, that's going to be a bit more writing, unfortunately, right? So if root, so we've got this as tree A and tree B. So if tree A is equal to null, and tree B is null, right? Well, I guess they're equal, right? They're both null, actually. They're equal. They're equal, right? So I'll return true. On the other hand, what if one is null or the other is not? So if tree A is null and tree B is not equal to null, return false, because they're not equal. One is null, the other one's not null. So, and then the reverse is true as well. If tree A is not, if tree A is something and tree B is null, return false as well. Other condition is that they both have something, and now we actually have to do some work, right? So first, let's check if the items are the same, or if the nodes are the same. So you can do either, in this exam, I would accept either this, which is if tree A equal tree B, or tree A dot equals tree B, right? Or honestly, but technically what you're looking at is if tree A dot item equals tree B dot item, or dot equals, Doesn't really matter in this case. The dot equals versus the double equals distinction. I'm not really caring about that in this case. So if their items are equal, right, because that's what we care about is the data stored inside of them. If their items are equal, then that's good. Then we don't know our answer yet. But if they're not equal, so I'm changing that to a not equal, but then I know something. I can return false immediately, right, because they're not equal to each other anymore, right? So if they're not equal to each other, return false. Otherwise, I have to do more work, unfortunately, right? So those two things are equal. Great. Now that means I have to check their left trees and their right trees. Okay, but so let's see, Boolean. So, but that just means I just need to do this recursively. So Boolean left equals is equal to tree A dot left, tree B dot left. Okay, and then right equals is equal to equals on the right sides. So we check the right. So we check if the left sides are equal, and we check if the right sides are equal. And that's all we have left to do. Well, so now at this point we can return. We can do our last return statement. We can return left equals and right equals, and then we're done. So basically, so we check if the left sides are equal. We check if the right sides are equal, and then we AND them against each other. If the left side, if both of these sides say they're equal, then we'll say, okay, my two subtrees are equal. And if one side is equal but the other's not, then the whole tree is not equal, so we return false. Make sense? So really, there wasn't too much code in there. There were just a lot of cases, right? Yeah.
Theoretically, you could get rid of the cases where one is null and the other isn't null, because like eventually, the
Right.
bottom statement has to return that.
Right, but over here, the reason it avoids me hitting a null pointer exception.
Okay.
That's kind of the reason I have to do that. I have to avoid hitting a null pointer exception when I look at the dot items over here.
Null pointer.
Right. So yeah, because if I try to do tree A dot item and tree A is null, then I'll generate a null pointer exception.
Okay.
But I mean, on the exam, you'd probably lose a point for that. But it would just be an annoying thing that keeps happening in your actual code. User settings. Let me raise the Okay. So that's definitely the hardest tree question. That's really a really hard tree question. But notice it's the same exact structure. Figure out your base case, or in this case, it was base cases, right? And then do the recursive case. Figure out myself. Figure out my left side recursively. Figure out my right side recursively, right? And the only difference is that I pluralized sides there, right? But there wasn't anything too difficult. The left sides go with the lefts. The right sides go with the rights. So the structure is the same. So now last coding problem on the exam, and then we've got a couple of theory problems. I'll have two on the actual exam, but they aren't too brutal, I'm hoping. So this one I made a mistake. I'm so sorry, but this is what happens when I try to write it. As I mentioned, this is what happens when I try to write with children running around, and trying to pay attention to them and half working on this. And it's supposed to be a string word. And what this is that we are trying to remember, maps are pretty much good at two things, which is categorizing and counting, right? Counting how often arbitrary things occur, maps are good at that. And categorizing things, with the key being like a category and the value being a list of things that go into that category or a set of things that go into that category. Maps are good at that as well. So maps are really good at categorizing. So this one, it says we write a method which characters occur in a string and how many of each. So it was supposed to return, or was trying to say was write a method which returns, that what characters occur in a string and how many of each. So here, this is the classic case of counting stuff for maps, which is that I'm counting the number of characters that occur in a string, and the value is how many times that character occurs. So let's go through and write a loop to iterate. So we're going to iterate character by character of word. So, and we're going to put those into a map. And I'm going to ignore the generics for right now, because why not? It's an exam. I can always go back and put them in later, but shortness is here. So map is equal to a new hash map. Okay, and then for character, so for each character C in word.toChar array, to turn it into an array, so I can just do a for each loop because I don't care about the index. Right? You could just do the simple for int I is equal to 0, I is less than word.length I plus plus, and then inside of it have char c is equal to word.charat I, but this is shorter. So for every character, now there's only 3 methods that you really ever need to remember how to do for contains, for maps, right? You want the contains method to know if a key is in there, put to put a key value pair in there, and get to get the value associated with the key. I don't think I'll ever ask a question that requires you to actually delete something from a map, but that's, I guess, the 4th thing there. And technically the 5th thing is empty, but that's not really too useful to all the time. So, and yeah, you can iterate through all the keys by using something like the key set, but I would give that to you on an exam. The ones that I expect you to know for maps are put, get, and contains. So first off, in our map, our question is, have we seen this character before? Contains, if map.contains our character C. If we have seen it before, and we haven't seen it before. So let's start off with the if we haven't seen it before. If we haven't seen it before, which is our else condition, or you could make it your first condition by putting like the not over there, but whatever. But if we haven't seen it before, then we've seen it once now, so we'll want to put that into our map. So map.put C, and we've seen it once, right? Because the value is the number of times we've seen it. If it's not in the map, well, then we've seen it once, right? We've seen it once now. Put that into the map. So if we have seen it before, though, we've seen it another time. So let's go and see how many times we've seen it so far. Times seen is equal to map.get C. This will get how many times I've seen it. And then I'll want to update that value. And you can update it by doing using the put method. Map.put C times seen plus 1, right? So we've seen it one more time, and we put that into the map. And that's it. Nothing else. There's literally nothing else. Maps are, once you understand how the map methods work, they are really easy. I highly recommend going onto CodingBat and looking at the map problems they have there. They'll be extremely helpful if you're struggling with this. But maps are really easy. Now, I will have a map question on exam 2. We're gonna have a discussion today among the 2168 instructors whether or not we are going to be including maps in the final. We haven't in the past. I really want them to be in the final exam. But there's also we've also in the past asked questions where you don't need to know maps and sets and how to use them in the final. But knowing them makes the problems a whole lot easier. Like it reduces them to 8 lines of code rather than 16 or something, or even 4 lines of code. It makes it really easy and conceptually easy to solve a lot of harder problems, right? If you're just trying to count the number of times things occur, which is like useful for even for checking if things are permutations of each other, right? Or things are unique, right? Sets and maps are the ways to go. And your problem is on the exam will be similar to this. Okay. Analysis. How would a Huffman tree look if all the symbols were equal? In other words, if the weights of all the symbols were equal. Yeah. What was that? Was that?
Look like what's the name?
Perfect?
Perfect tree, but at the same time, it was also each of the
Right.
values would be half the original you get down.
Right. They essentially all the stuff would be on the leaves, right? And all the leaves would be about the same weight. And this is because with the Huffman tree, basically you're gonna build, you're gonna build one set of leaves, then another set of leaves, then another set of leaves, and you're gonna combine the sets of leaves, and you're gonna combine the sets of leaves, right? In something that's completely equal. If the weights are completely equal, it's gonna look like this. And this was a question I think I asked on exams in the past, but I'm not asking a Huffman tree analysis question here. So if we've got a bunch of characters over here, right, they're all going to essentially be on the same weight. And this is not what's optimal for a Huffman tree. Why? Because for a Huffman tree, we're trying to encode characters on different lengths. And if they all appear at the same frequency, then it doesn't really make sense.
That's just the binary tree, right?
Right. They're going to be essentially on the same level. Right, they're all going to have the same length of bits, the same number of bits to encode each of them. Even though technically with 4 it would be shorter, but I mean, if all if all 128 characters had the same frequency, like the ASCII characters had the same frequency, then you'd still be using 7 bits to encode them.
And you could of course draw this on the page.
Yeah. So, and then these two go. Let's see. What is these are questions from an exam. These are also questions I asked in an exam too. Oh, I didn't switch. Sorry. So that was the first question. So, and these next 2 questions are also questions I've asked in previous exams. But they're not going to be what you get on this exam. So, what is the average runtime of insertion and deletion algorithms in a binary search tree and why? And so because we kind of dove into self-balancing binary search trees, I got to add the caveat that these are not self-balancing trees, right? These are the trees we learned to collapse. What is the average runtime for insertion and deletion? Let's start there. So how long on average, what's the big O time that we expect to see in a tree? Log n, yeah. So why is that log n? Location, right? You're going, because it's going to take h number of steps, where h is the height of the tree, right? And if we assume that it's relatively balanced, then you're looking at, to the h kind of nodes in there, right? Now, and it's log of n, because every time you go left and right, if it's balanced, then basically you've eliminated half your search space. Okay. And then what is the worst case runtime for insertion and deletion algorithms in a non-self-balancing binary search tree? O of n, right? Because worst case scenario, you add 1, then 2, then 3, then 4, then 5. Essentially, your binary search tree becomes a linked list, which is really boring. So that's what we've got there. So your not your final, but your second exam will be tomorrow or on Friday, depending. Good luck with it. It's not too bad. Again, if you thought this was okay, and if you think you could solve the coding problems, then you'll probably be fine. I find that there are a lot of cases where the second exam scores are higher. Maybe it's an indication that I need to make a harder second exam, but I feel like there's just enough content on it already.